All right, so now let's look at radiation and look at the different types of particles that are released. The different types of particles. The first type of particle, I think we use Serenity as an example. Remember that she was going about her business and then she blows up, giving off a piece of flesh. The pieces of flesh are what we're talking about. First type is alpha rays.
Ernest Rutherford confirmed that radioactivity involves three different types of radiation: alpha, beta, and gamma. Alpha radiation consists of positively charged helium nuclei, that is, 2 protons and 2 neutrons. The radioisotope americium-241, used in smoke detectors, emits alpha particles. The parent nucleus contains 95 protons and 146 neutrons, making a total of 241 nucleons. When an americium atom decays by ejecting an alpha particle, the remaining nucleus has only 93 protons. This is a new element called neptunium-237. The decay equation looks like this. Neptunium-237 has 2 less protons, 2 less neutrons, and 4 less nucleons overall. Positively charged alpha particles are affected by magnetic and electric fields, but because they are relatively heavy, they are only weakly bent or deflected. They have low penetrating power and are absorbed in a few centimeters of air or by a sheet of paper.
All right, so alpha particles. What is it composed of? Basically 2 protons and 2 neutrons. In essence, they are the same thing as a nucleus of a helium atom. These are huge. They are monstrous. They are 8,000 times larger than the other type of radioactive particle, which is called the beta particle. It's huge, but a few centimeters of air can stop it. And your skin definitely stops it. They are bowling balls, but they can't penetrate your skin. Their biggest danger is if they get inside your body. If you breathe in a little Serenity, and inside your lungs, Serenity decides to blow up, giving off an alpha particle, then you've got a bowling ball inside of you. Then you can have some problems. Yes. But outside, you can rub yourself with Serenity type particles. They won't hurt you. They won't hurt you. Just don't take that hand that you've just used to rub and stick it in your mouth. Or try to breathe it in.
Wait, so is that number 10 inside your body?
Okay, so basically, you have 226 protons and neutrons. If 2 protons and neutrons decide to just take off and leave, then you've got it yourself an alpha particle. It's symbolized by the little lowercase a, which looks like a fish. So what's left over is something that has 2 protons and 2 neutrons less. It's a brand new person. It's not radium, it is now radon. The problem is, just like we used when we talked about Serenity, is that radon itself is radioactive. So we don't know when, we don't know why, but at some point, radon is going to blow up, giving off, I think, 2 protons, 2 neutrons. It could give off a beta. We'll see here in a little while. Where can alphas cause the most damage? Inside your body. in your blood or organs, especially your lungs. All right, so this is called a nuclear symbol. Radium is number 88, helium is number 2, radon is number 86. Notice it adds up. 226 becomes a 4 plus 222. Yes? Does that add up? Mm-hmm. Yeah. How about 88 becomes a 2 plus 86? Mm-hmm. Yeah. So the next type of balancing equation is going to be the easiest type. All you have to do is make sure that they add up on both sides. They have to add up on both sides. All right. So what other type of radiation can we have?
The second type of radioactive decay is beta decay, which simply emits electrons. It has somewhat higher energy than alpha radiation, but it can still be stopped by a sheet of aluminum foil or even the top layers of your skin. So that thorium-234 that formed when uranium underwent alpha decay, it can continue to decay on its own, and when it does, it undergoes beta decay, releasing an electron and an atom of xenon. Notice that, again, the way we write this is a little different. Even though the thorium emits an electron, we don't use the usual symbol for electrons. Instead, we write it in nuclear notation form with the mass number at the top and the atomic number at the bottom. Since it's an electron and not a proton, we put a -1 for the atomic number. That probably seems a little bit weird right now, but next week when we talk about nuclear equations, you will see why it is useful.
All right, back in the early 90s, a really funny movie came out from the creators of Kindergarten Cop. It was called Twins. In it, it describes an experiment that they tried back in the 1950s where they took this beautiful, extremely creative, artistic, musical woman and they joined her egg with the combined DNA of a super athlete and a super genius. Okay? And so you had an egg that was combined and they impregnated the lady and she, to their surprise, gave birth to 2 people. Gave birth to a beautiful, healthy, gorgeous baby and a scrawny, ugly baby. And what they thought had happened was that the cells broke up and the crappy part of all the DNA, the genes, were what the ugly baby became. So they sent the ugly baby to Chicago to be a foster child, and the beautiful baby they kept in the South Pacific Island where they gave him the best education and the best diet and the best physical exercise that you could have. So the beautiful baby became Arnold Schwarzenegger, and the ugly baby became Danny DeVito. If you know who I'm talking about. He was Penguin in the Batman movies. He's been in a lot of movies. He always plays this ugly, nasty character. Okay? So, when Arnold became 21, they told him the truth, and he decided to go off back to America and find his long-lost brother, who was the crappy part of the DNA. And eventually finds them, and eventually convinces them that they were identical twins. So it's a funny, funny movie. But this kind of reminds me of this, because in the nucleus, there are neutrons. And neutrons are made up of mostly protons with a little bit of Danny DeVito, which is the electron. Okay? So during beta decay, what happens is Danny DeVito takes off. And what's left over is the proton. Okay? So a beta particle is the negative nastiness that's inside of a neutron. And when it goes off, Is it an electron? Not really, but it has all the characteristics of an electron, so we say that it's an electron. It's the nasty, negative nastiness that's inside every neutron. Every neutron is made up of beautiful proton-type stuff and a little bit of nasty electron. That's what is given off. So, what are beta particles? Fast-moving electrons emitted from the nucleus during beta decay. It is much smaller. Imagine Arnold is like 6'3", Danny DeVito is like 5'1", 5'0". It is much smaller, but it's so fast that it can penetrate far deeper into things. But because they're so small, they cannot do as much damage as the alphas. Danny DeVito grew up to be, the character grew up to be a con artist. So he was really quick on his feet. He was a scoundrel. But, you know, he was still a tiny little guy. Arnold could do a whole lot more damage, but Arnold was not as bright. Well, I mean, he was extremely intelligent, but he wasn't as sharp as Danny DeVito, who had a way of getting into things. So what exactly happens during beta decay? A neutron is transformed into a proton and an electron. The proton stays in the nucleus. The electron is ejected, becoming the beta particle. So, a neutron containing one proton plus neutron and no protons becomes a proton. This still stays one because even though a neutron has become a proton, it's still protons plus neutrons, so it doesn't really change. But now you have a proton. And think of a beta as the opposite of a proton. Do both sides add up, Emily? Look at it. 1 equal 1 plus 0? Does 0 equal 1 minus 1? Yeah. Nuclear reactions add up. Here's an actual example. 210, 82 lead. Notice that the 210 stays the same because a neutron becomes a proton, so it doesn't change the number of things. But notice that the number's gone up because now you have an extra proton. And then the beta particle is symbolized like this so that it adds up on both sides. Gamma. Oh, here's another beta explanation.
Beta radiation consists of high-energy, negatively charged electrons, which are produced in the nucleus when a neutron changes into a proton and an electron. The electron produced is the beta particle. For example, cobalt-60 is a beta emitter used in medical radiotherapy, equipment sterilization, and irradiating foodstuffs. Here is the decay equation. Cobalt-60, with 27 protons and 33 neutrons, a total of 60 nucleons, emits a beta particle, or electron, and the daughter nucleus is nickel-60, with 28 protons and 1 less neutron. The total number of nucleons remains unchanged. Like alpha particles, beta particles are affected by magnetic and electric fields, but are lighter and more easily deflected. They cause less ionization than alpha particles, being smaller and with a single charge, but they can penetrate further. It takes several centimeters of aluminium to stop beta particles, and they will travel for a few meters in air.
All right. So how do these guys usually leave the nuclei? In excited state. In excited state. What usually is given off along with the particles? Energy. Remember talking about serenity again. She would give off a little piece of flesh and what? There would be light. The light is what we're talking about here. Most of the time, not all, but most of the time, when a particle is emitted, there is also gamma radiation given off. Gamma radiation given off. How does gamma compare with alpha and beta? Gamma is pure energy, my friends. It is pure energy. So it will go straight through you, but it can't affect, it's microscopic compared to an electron, and an electron is microscopic. It doesn't affect as much stuff. So it'll go straight through you without touching anything, but every once in a while it might touch something, and if it touches it, it wipes it out. It ionizes it. So your problem is that you are constantly being exposed to gamma radiation. Yes, the gamma radiation goes straight through you, but every once in a while it might do some damage. And a lifetime of exposing yourself to gamma is going to cause some damage, maybe cancer. Can't hide in a cave because there's actually more radioactive materials in caves than there are in the open air. Can't hide in the open air because then you're being hit with ionizing radiation from the sun. It's going to be still in the air. I'm sorry, you're going to die. You're going to die unless you get run over by a carriage like Pierre Curie. You're going to die. Okay? I'm sorry. I hate to be a bummer. Am I the first teacher to tell you this? Yeah. I'm so sorry, but it's the truth. At least I am honest enough with you to tell you the truth. You're all going to die at some point. And if you live to be old enough, like in your 90s, you're going to probably die from radiation damage over a lifetime. Here's gamma radiation.
Gamma radiation is a form of electromagnetic radiation, like radio waves, heat, and visible light. It is found at the highest frequency end of the electromagnetic spectrum, after X-rays. Gamma rays are produced in the nucleus as part of a rearrangement of energy levels after the emission of an alpha or beta particle. For example, when a uranium-238 nucleus releases an alpha particle and decays to thorium-234, a gamma ray is also produced. Having no charge, gamma rays are unaffected by electric and magnetic fields. They have low ionizing power compared to alpha and beta particles, but being photons, or packets of electromagnetic energy, are the most highly penetrating of the nuclear radiations. Gamma rays are mostly, but not completely, absorbed by a lead shield several centimeters thick.
All right. So, let's review. Alpha is the same thing as a helium nucleus. The atomic number goes down by 2 because the number of protons go down by 2. The number of neutrons go down by 2 because the number of neutrons go down by 2. This number here is the sum of these two things, so that means it decreases by 4. Beta particles, it has a symbol of 0, -1. The number of protons go up by 1 because what you're doing is you're converting a neutron into a proton. But because this number is the sum of protons and neutrons, there should be no change. And then gamma is just pure energy. It doesn't have a symbol. It's not a particle. It doesn't have a symbol. So, alpha particles are going to be stopped by your skin and by paper. Beta is going to go straight through paper, but it's going to be stopped by something much denser like aluminum. And then gamma will go straight through. You're going to have several inches thick lead in order to stop gamma. X-rays are similar to gamma, so when they take an X-ray of you, what do they usually give you for the rest of your body?
Cover.
Yeah, and guess what that cover is made up of? Lead. All right, so let's get back to Serenity. Uh-oh. Let's get back to Serenity. All right, remember we told the story of how she became different people. A decay series is all of the different people that Serenity will become until finally she becomes somebody who is no longer radioactive. So a decay series kind of gives you the genealogy of Serenity, the story of Serenity, of all the people that Serenity eventually became before she finally became somebody that is no longer radioactive. All right, so here's the story of Serenity. Serenity was uranium-238. She gave up 2 protons and 2 neutrons. Now she looks at you and goes, I'm thorium. I'm thorium. After a while, a little beta particle goes off. Beta. And now she says, I'm protactium. And then, I'm uranium. I'm thorium again. I'm radium. I'm radon. I'm polonium. I'm lead. I'm bismuth. Polonium. And then she could actually take different tracks. It becomes a little more complicated. She could go from bismuth to titanium, or from polonium to lead, and then eventually lead 206. According to scientists, it takes 4.5 times 10 to the 4.5 billion. 7th years. 4.5 billion years for Serenity to go from 238, for half of Serenity to go from 238 to lead. So if we were to put Serenity in a box, and there would be like 30 Serenities, after 4.5 billion years we would open the box, and half of that stuff in the box would be lead, and the other half would be any one of these elements along the way. After another 4.5 billion years, 3/4 of them would be lead, and the other would be any one of these guys along the way. Okay, notice the problem here. We live in an area of the country that has a lot of uranium in it. Not a lot, but some. Notice along the way, who does uranium become? Radon. Radon, unlike all the others, is a gas. So as soon as radium becomes radon, radon starts working its way through the soil or through the rock and comes out and gets into our air. That is why radon is our #1 problem when it comes to radioactive substances. The #1 cause of lung cancer in the country is what? No, not radon. They're #2. What? Cigarette smoking. Yes, cigarette smoking is #1. But #2 is radon. That means all of us can potentially get lung cancer. Don't get surprised. Don't get all huffy with your doctor if he looks at you or she looks at you and says, "I'm sorry, but you have lung cancer." Don't get all defensive and say, "I have never smoked in my life." Did you breathe? Yes. Then it's probably from radon. Since when have we had trouble with lung cancer due to radon? Since the beginning of time. When did the public become aware of this? Actually, it wasn't until the 1980s with the advent of energy-efficient homes. When we started closing things up, the amount of radon started increasing. Why? Because where could the radon go when you have very efficient homes?
Heaters.
Nowhere. You see, back when it wasn't efficient, the people used windows. Have you heard of those things? Windows that you open and allow air to come in. When that happens, then the radon gets out. If you never open the windows, just like those windows we have here in this room that never open, then there's nowhere for the radon to go. It seeps in through cracks in the basement. So if you sleep in the basement, how do old homes compare with new homes? Much less. Why? They're not as tight. They're not as efficient. They have far less radon. How is it dangerous to us? Well, Jeff, who sleeps in the basement, breathes it in. He's okay as long as he breathes it out. Radon is heavier, so he's going to have to take some deep breaths in order to get it out. But what happens if radon blows up while it's inside his lungs? Then it becomes a solid again, and now he's stuck with it. So we all have heavy metals in our lungs that are there because when we breathed in radon, it blew up. We were just really unlucky, and it blew up. A scintillation counter is a probe that contains a substance that emits light when ionization radiation hits it. This is an alternative to a Geiger. It does better with gamma radiation. How can a radiation worker know if they've received too much radiation? Have you seen people around town with these little badges on them? Okay, those are the badges. They have a film inside of them, and when a radioactive particle or gamma hits it, it develops the film a little bit. So every month or every 6 months or so, they'll pop open this thing, develop the film, and depending on how dark the film has become, they know how much radiation you've been exposed to. Even secretaries out at Y12 wear these things because even though they're not playing around with the stuff, they're still in an environment that has a higher than normal radioactivity. So what happens to a worker if he's exposed to too much radiation? In January, they're usually just taken off their job and made to work in an area that is low radiation. So you could go in and have to clean up a waste spillage site and get all of the radiation that you're allowed for the year in the first week of January, and then basically you are no longer working your job for the rest of the year. They have to put you in a safe zone for the rest of the year. So they may have you sweeping up floors or whatever. You're done. You're done.